Hello everyone. My name is Viju Putanveetil, and I am just completing my research in artificial intelligence and machine learning from LJMU. And today I am presenting my research work for my master's in AI and ML. The topic of my research is EmoNet, a transformer-based network for conversational emotion recognition. This is a novel framework and architecture that I am introducing for emotion recognition in conversation, or simply we can call it as ERC task. So let's move on and yeah. So the agenda for this talk is given here. So let's move on. So why did I choose this topic, and what was the motivation for me, and what is the background? So here the ERC task. So it has huge potential in enriching the understanding of human-machine interactions. So it also opens up and advancement in various domains, including customer service, mental health, and education technology. There are so many other fields where the emotion-aware interactions uh, give benefits. So it has a potential to enhance the emotional intelligence of missions, and thereby it will revolutionize the way we interact with the technology. Also, integrating ERC leap forward, creating more empathetic and responsive AI systems. The current state of art in ERC for the dataset I selected, that is Emory NLP, has a score of 41.39, and this itself indicates there's a huge scope of improvement in this field. That was the motivation, and also actually I like to explore the emotions, people emotions in their conversations. So that is also my personal interest for this topic. And what is basically ERC, or emotion recognition in conversation? Here, the aim of this task is to identify the emotions when a speaker is speaking. So we get a speaker's name and its utterances and predefined emotions. We need to classify the utterance from a speaker to the emotion classes we already have. You can see these dialogues from the TV show. I think everybody knows that TV show Friends. So how the emotion changes across the dialogues. These dialogues contain two speakers. So then literature review. So I have reviewed the current state of art literature review. The basic purpose is to understand various architectures researchers already explored, and see what all the technologies they have tried already, and what are the most prominent technologies, and the methodologies they use. So we see most prominent today is transformer-based models and GCM, and previous era we can see CNN, GRU, LSTM, and many more. So the methodologies, we can see the common sense knowledge, curriculum learning, hierarchical, self-attentions, and many related technical methodologies people adopted. And the other observation through the literature reviews, the models are getting complex, but the relative gain in prediction is uh, not that significant. And we can see the current state of art in ERC for this particular data set is 41.39. So out of the state of art models, I have selected one model called CompM. This I find relatively simple to explore, and I find it's like there is opportunities I can contribute. That was my literature review. Research questions, what I have is that by seeing the current score, how can we improve the performance of emotion recognition? And is there any possibility of novel architecture and techniques uh, and uh, and is there any possibility of enhancing current model? And is there any gap I can fill in? So, and other questions I have is what are the are there any specific aspects of conversation that existing model fail to capture adequately? And how can we address these limitations to achieve higher accuracy? And what are the potential limitations or biases in the existing state-of-art models for emotion recognition? And we can address any of this. So those were my research questions. And the method I followed is first collect the state of art data set, that is emotion detection data set from Emory NLP from their GitHub. And this is basically the textual conversation from the TV show. And it is labeled with 7 labels based on uh, emotion from feeling wheel paper. And one additional emotion label that's neutral. What I did is I did feature engineering, basically extracted the relevant features, that is speaker name, utterances, and the labels, out labels. So this I engineered into input uh, um, the the novel model I introduced, and tokenize these engineered features, then input that um, to the EmoNet. And within EmoNet, I used Robota and GRU. And it's trained on a 6000 GPU with 48 GB hardware on Linux VM. And this was from a cloud provider. And the evaluation metrics used is weighted F1 score. That is the standard among the multi-class classifications. And the state-of-art leadership leaderboard use this is to rate or rank the relative performance of the model. So I go with the same metrics. So this is the EmoNet architecture. We can see at the bottom, there's a dialog context, that is one module. And at the mid right, you can see the another set of boxes that represents the second module. So here, this also explains with an example where a dialogue with the 6 utterances, and we are currently processing the 6th utterance, that is U6, and that is spoken by speaker A. So at the bottom right, if you see, we have dialogue context. So for the sixth utterance, that basically comes with the speaker name, utterance, and label. So we have this dialogue context. So what it represents is that from the leftmost bottom, we have a classification, a special token that is used for classifier. Then we have speaker and utterance in that combination for all the previous utterances within the dialogue. So first utterance is done by speaker A, then speaker D with U2, and speaker Y with the U3, then again speaker A with U4, then speaker A uttered U5, then currently the current speaker USA is processing U6. So that basically this is basically tokenized using Roberta tokenizer. That is a Roberta is pre-trained language model, and we tokenize it and train it for the context understanding. Then if you see at the mid right, we can see the current speaker is A. So we are trying to model the speaker behavior of the speaker A. So the thought process behind this is like it's not only the utterances in the context, dialogue context, that makes up speakers' emotions. It could be probably also from his behavior or personality. So to model that, I'm using all the utterances speaker had before in all the conversation we come across. So so just explaining this block, let's see the topmost blocks. We have utterance history. So what we are doing here is that we have speaker A, and you can see a list of utterances that happened, that is uttered by speaker A. From this includes the utterances in this dialogue as well as all the previous dialogues from the beginning of whatever maybe we can say the system. So it is a list of utterances, and similarly all the speakers we identified so far in this system would be having its own utterance history. So in this example, though we have other speakers that we can see in the dotted form, the top right, we represent, we can see here I have listed the speaker A, D, and Y, and you can see that this is not uniform. It depends on how many utterances speaker had in the past. So and so that is utterance history. So that is a global kind of data. So all the dialogues, this dialogue as well as then coming dialogues also will be having access to this utterance history. Now come back to the mid right block. See, for the speaker behavior, we have taken utterances of speaker A from this dialogue as well as the historical utterances. So this is given to the pre-trained language model. Here, my choice was Roberta. Then the output of these would be given to GRU, that is the lowermost block of this speaker behavior. And this GRU output is again concatenated with the dialogue context output, the robot output from the dialogue context. Then we will be having a W0, that is the probability distribution of the class. So the one which is having the highest probability value would be the selected emotion set for this utterance. That is, in our context, this is U6. So we will determine the probability, the means emotion level for U6 as the W0's highest value in the W0. So this is the EmoNet, and this architecture is extendable. Maybe I will touch up of this thing in the coming slides whenever an opportunity occurs. So this is end-to-end solution framework. How the system works. So here we have a raw data. So this is raw data from the GitHub locations. We get it from my manual download and we pre-process it. So we need only three features, one output features and two input features. That is, speaker input features are speaker name as well as the utterance, and we transform it. So we pre-process and transform it, and we select the the input feature, input raw data is in JSON format. We make it to text format and we select only the needed features. Then next block we can see the data loader, and it basically do the feature engineering, basically convert this speaker and utterance into the dialogue context, as well as the speaker behavior things. So then batching happens. So here our choice of batch size is 1. Then we need to input this into the EmoNet. So before that, we need to tokenize it. So we tokenize with the Robota tokenizer. So you can see the output of the third block is 3 things, like 3 items. So we have input tokens. So that is the input for the context model in the previous block. And that is the first module. And we have speaker tokens, that is the input for speaker behavior, and label represents the emotional labels from the data set. So we train this based on the configured epoch, and during training we also try the development set to see the our evaluation metric score on dev set, and out of all the epochs, whichever epochs we get the best dev score, that we select that model, we save and use it for our as a final output, model output. This model output is used to find test score for the test set. So this is a end-to-end framework. Let's move on to the next slide. So here, this is the results. So we have performed various experiments to come up with this model. So I started with the our base model, that is to find what is the performance we are getting from the base model CompM, and we got 37.85. That is little okay. Then we introduced global speaker identity. If you see in the our base model, it has knowledge, speaker knowledge for within the dialogue. So once we move from one dialogue to another dialogue, there's no history of the speaker maintained. So basically, we will not be able to model speaker behavior or personality using this. So we need to introduce a global speaker ID. That was the thought process. And definitely, we know by introducing global speaker identity, the existing data set, or this gets diluted because speaker definitely would be more than but that is a needed change. Then introduce speaker behavior. So with speaker behavior, we basically take take the previous utterances along with the utterances of the current speaker within the dialogue. So with that, we train and we get near to the F1 score of the base model. So we are slightly improving from the impact of the global speaker ID. So, and the current so here, one more observation is that we are using loss function for training as a cross entropy loss. So our data set is not a balanced one. And because, see, in our normal conversation also, some extreme emotions won't occur so often. So it is never going to be a balanced data set. So some of the common emotions are more frequent, but the lesser or extreme behavior, extreme emotions are not that much. So, but we have challenge in class balancing because as we know, in a dialogue, we have a sequence of utterances and the emotion way changes gradually and these utterances are sequential in nature. So if you try to augment this data with more data or we try to remove some of the more frequent utterance emotion level set with this by removing the data, then we lose that sequential nature. So because of that, I did not do any data manipulation or augmentation to class balance it. But other ways like to introduce a weighted cross entropy loss. So with that less frequent class will get higher weightage during the back propagation. Whereas the high frequent level will get less weightage. So this will somewhat compensate the class imbalance. And I see 37.13 as a weight F1. So one more additional change I did is that I normalize this weight. So with that, I get 39.18. So if you see the second table, this bottommost table, we can see the relative position of the EmoNet score in SOTA state of art rank table for the Emory NLP. So EmoNet is 39.18. So this is just behind the 7th position, and the first rank SOTA is around 1.12, 1.21 points ahead. So you can see on right side the emotional recognition in conversation for Emory NLP, the evolution of the prominent models. So this graph shows from early 2020 till September 23, and the most performing state of art ERC model is instruct ERC, and it gets 41.39. So, so that is the result. And now comes the discussion and conclusion. See, we see the emotion understanding involves multiple cues like tonality, facial expression, body language, and many more. So in a real conversations, it's not only the word we speak, but also many other known uh, non-verbal communication happens, and that even builds the emotion of the speaker. And in textual conversation, textual data, we don't have access to any of these cues, and that is the challenge we face in this ERC task, where we have only the text data and emotion label. So the observation made for from this literature review was that the most of the research work emphasizes mainly on the dialogue context. So their emphasis is on the current dialogue, and it may not capture all. And since it has textual data, we don't have all the emotional or other cues. So it is limited that way. So behavioral model, by having all the previous utterances, will somewhat compensate and supplement this emotional understanding. Not definitely, it cannot um, compensate all the loss made from the other cues, but it supplement definitely on the contextual focus. Basically, the dialogue, current dialogue can have understanding of the current speaker's behavior. And if you see the future direction, the exploring new methods of using contextual and behavioral data can advance the emotion recognition system. So we can also model this on the other speakers in the conversation, their behavior and how it interplays. So that is one of the things. Even my research work is still going on that front, and I am basically modeling one more things on top of this. So, and I guess this would give a huge, good boost up in the score, emotion detection score. So what I'm trying to do is basically um, modeling the dominant speaker, okay, in a dialogue. So basically, we know in our personal experience also, is a dominant speaker in dialogue has a good or a great influence in the current speakers or all other speakers' emotions. It could be positive or negative, and so if you model that dominant speaker's behavior and find what is the influence of that in the current speakers, I believe that can improve the emotion detection. So the contribution to the knowledge. So what I have here in this research, I introduced a novel architecture for ERC on textual data. And the contributions are like, I propose that a speaker needs a global identity across all the data the model is exposed to, and this helps the prediction based on the past knowledge. So this global identity basically helps to model the speaker behavior and the current speaker behavior, so that is good influence on or maybe marginal influence on the emotions of current speaker. along with the context of the dialogue, his behavior or her behavior can also influence the emotion of the speaker. And propose weighted cross entropy loss to deal with the class imbalance. Maybe we can have a better, more better loss function to to um, deal with the class balance. We already saw out of our experiments that the weighted cross entropy itself is giving a good boost up in the F1 score. So these are the contributions. So the future recommendation, like the global speaker identity and speaker utterance history, this opens up new possibilities to investigate. Okay, basically, we can see how we can model the speaker's personality or at least the behavior pattern, and which zone the behavior of the speaker lies or goes around. So maybe this can contribute to the detection along with the speaker the context model. Then we can see the co-interworking of these behavior patterns and the influence of speakers on other speakers, speakers' behavior on other speakers. Rather than just looking at the trends in the current context. So what carries and probably a speaker's previous memory, memory with or experience with the other speakers in the past. So that also contribute. Maybe many other possibilities we can explore. And anyway, I will continue with my more modeling and on the dominant speaker behavior. And I hope that will contribute to the community and contribute to the knowledge base. So that concludes my session for my thing on this research work, and thank you for your patience and listening till now. Thank you.